This is the morning glory. It's a climbing plant frequently found in hedgerows. But what's it got to do with statistics? Well, we're going to look at some data collected about this plant. And from these data, we'll see whether the plant passes on some of its characteristics according to classical genetic theory. And we'll use the statistical idea of goodness of fit to help us. This is a normal type leaf. But other morning glory plants may also have leaves like this, variegated. If we cross a plant with variegated leaves with another of the same type, then we'll only get variegated offspring. Similarly, if we cross normal leaf plants only with other normals, then we'll only get normal offspring. So far, so good. But what type of offspring do you think we'd get if we crossed a normal plant with a variegated plant? I'll show you what happens. Each plant carries two genes which determine whether the plant is variegated or not. For simplicity, I'll denote the normal gene capital A and the variegated gene little a. So the variegated plant has these two genes, little a, while the normal plant will carry the genes capital A, capital A. Now, when these two types are crossed, the offspring inherits one gene from each parent. We don't know which of the two genes any individual offspring will inherit, but here are the possibilities. But what characteristic would we actually see if we looked at a plant with these genes? In fact, what happens is that in each case it would have an appearance just like a normal plant. And here's how I'll represent its appearance. So what's happening? Well, the presence of this normal type gene actually has the effect of masking out the variegated gene. So although the variegated gene is present, its effect isn't seen. We say that the normal gene is the dominant one, and the variegated gene the recessive one. And what we see is called the phenotype of the plant. But what if we now take two of these types of plant and cross them? Once again, the offspring inherits one gene from each parent. The theory says that genes segregate independently. This is known as Mendel's first law. Moreover, there's a 50-50 chance of the offspring inheriting either one of the two genes. So here are the possibilities. And each of these four possible outcomes has a probability of 1/4 of occurring. So what would these offspring look like? What would be their phenotypes? This is like the normal plant we started with. It's got the normal leaf. This is like each of these parents. It has this dominant gene and so appears normal. This one is the same. Which parent the gene comes from doesn't matter. But this one has both variegated genes, so it appears variegated. So by Mendel's theory, we'd expect 3/4 of the offspring from this type of cross to appear normal, and 1/4 to be variegated. Of course, plants have more than one gene pair. They have lots, corresponding to lots of different features. Now let's introduce a second characteristic. Another pair of genes determines whether or not we get a faded leaf. We'll call these genes capital B for normal and little b for faded. Again, this is a characteristic where the normal gene, capital B, is dominant to the recessive faded gene. Now we're going to investigate a cross between a mixture of these two characteristics. Again, both parents will appear normal because both possess the dominant genes. Here's how we represent them. This parent carries both the normal and variegated genes in this pair, and also the normal and faded genes in this pair. The other parent is exactly the same. Now, Mendel formulated a second law to determine how this type of cross should work. This says that inheritance of one characteristic is independent of the inheritance of any other characteristic. What this means, if it's true, and that's what we're going to use statistics to test, is that the way the A genes segregate should be independent of the way the B genes segregate. So, assuming this to be a reasonable model, we should be able to infer that there is a probability of 1/4 of this parent passing on any one of these combinations to its offspring, and the same probability of the other parent passing on any of these 4 outcomes. So, what types of offspring should we get? Well, here they all are, 16 types of segregation in all, and each one should have a probability of 1/16 of occurring. But what we're concerned with is how these offspring would appear to the eye. Now, all in all, out of the 16 possible segregations, 9 of them turn out to be normal. That's capital A with capital B. 3 are variegated. That's little a with capital B. 3 are faded. That's capital A with little b. Finally, just 1, little a, little b, is both variegated and faded. So, if Mendel's second law holds, those are the proportions 9, 3, 3, 1 we'd expect to get if we carry out a large number of crosses.
Here's the result of one experiment on morning glory carried out in 1931. From a total of 290 offspring, they observed 187 normal plants, 35 faded plants, 37 variegated, and 31 both faded and variegated. The question I want to ask about these data is, does the model that we've been looking at fit them? The theory indicated that we should expect to obtain results roughly in these proportions. So we'd expect about 9/16 of the 290 offspring, that's about 163, to be of this type, normal. They actually found 187, a discrepancy of 24, and similarly for the other 3 types. Here at last is our goodness of fit problem. We want to know whether the expected values are an acceptable fit to the observed frequencies or counts. To give us a clue how to tackle this example, let's leave it for a moment and see what we can do with a simpler invented problem with just 2 counts instead of 4. This will enable us to relate our problem to a technique we've already met. It's been well known for many years that only 20% of the population of Ruritania know the name of their Prime Minister. Following a change of government, a new survey's just been carried out. Here are the results hot off the press. It was quite a small survey. In all, just 100 people were chosen at random and asked the name of their Prime Minister. 27 got the name right, 73 got it wrong. Is it still reasonable to assume that only 1/5 of the population as a whole know the name? Once again, It's a question of goodness of fit. Could the expected values of 20 and 80 be a reasonable fit to the observed values 27 and 73? If our observed values had actually been 20 and 80, we'd have had absolutely no reason to doubt the underlying figures of a fifth, 4/5. If our observed values had been 21 and 79, or for that matter, 19 and 81, we'd still have no reason to doubt them. At the other extreme, the 100 people surveyed might have split 0 and 100. With the underlying 1/5, 4/5, this would have been just possible, but very, very unlikely. A probability of 2 in 10,000 million. We'd certainly doubt the 1/5, 4/5 figures then. But our values of 27 and 73 seem to be in the grey area. So how should we assess the goodness of fit? In some sense, it's really measured by the deviations of the observed from the expected values. The smaller the deviations, the better the fit. But is this the whole story? Let's see. Here are the deviations. 27 minus 20 is plus 7. 73 minus 80 is minus 7. Now, remember, what we want is an overall measure of goodness of fit, not just for this value or for this, but for the data as a whole. So we must combine these in some way. Clearly, we can't just add them together. We'd get 0. Well, to stop the plus and minus cancelling out, we could square these deviations and then add them. Would this give us a suitable measure? No, it doesn't, because it doesn't take into account the size of the sample. Look at these data instead. Suppose we'd asked 1,000 Ruritanians instead of 100, the name of their Prime Minister, and got these results. 207 right, 793 wrong. The expected values are now 200 and 800, but the deviations are the same as before, plus 7, minus 7. But plainly, this is a much better fit than the set of 100 observations was. So we need to scale the deviations in some way so that these data show us a better measure of goodness of fit. I'll tell you the method straight away and justify it a little later. We square each deviation d, getting d squared, and then divide d squared by the expected value e. The sum of these d squared over e values gives us our measure of goodness of fit. Here it is. Taking 80 as the common denominator, we get this, which simplifies to 49 over 16. For the 1,000 observations, we'd have obtained 49 over 160 as our measure of goodness of fit, only a tenth as much. So now we have a measure of goodness of fit. A value of 0 means a perfect fit, while larger values indicate a progressively worse fit. So what's the range of values which indicate a reasonable fit? What we do is to test our value as a value from the chi-squared distribution with 1 degree of freedom. If the value is so large as to be statistically significant, then we conclude that the model is not consistent with the data. Now, why does this method work? To answer that, we look at this same problem in a different light.
Here's the data. 27 right, 73 wrong. And here are the probabilities we're aiming for. What we'd like to know is whether the 27 correct observations are consistent with a probability of 1/5. We can think of each observation as being the result of a Bernoulli trial with probability 1/5 of success, 4/5 of failure. And all in all, there were 100 Bernoulli trials. So we can now ask, is a value of 27 consistent with the binomial distribution with parameters 100 and a fifth. Because our number of observations is quite large, we can approximate this binomial distribution by a normal distribution, where mu and sigma squared are the mean and variance of the corresponding binomial distribution. The mean of the binomial is NP, which is 100 times 1/5, or 20, and the variance is NPQ, which is 100 times a fifth times 4/5, or 16. So now we want to test whether a value of 27 is consistent with normal 20, 16. This is now looking like a familiar problem. If we want to know whether x is consistent with normal mu sigma squared, we can equivalently test whether x minus mu over sigma is consistent with normal 0, 1. So, entering our known values and simplifying, our test becomes, is 7/4 consistent with the standard normal? So here we're testing 7/4 as a value from normal 0, 1. Before, we were testing 49/16 against chi-squared 1. Have we got a different test? No. In fact, the two tests are the same. If z is standard normal, then we know that the distribution of z squared is chi-squared with 1 degree of freedom. So, rather than test whether 7/4 is consistent with normal 0, 1, we could test whether 7/4 squared is consistent with chi-squared 1. And this is the same as testing whether 49/16 is consistent with chi-squared 1. Here's the chi-squared distribution with 1 degree of freedom. The critical region of this distribution will be in this right-hand tail. And here it is for a significance level of 5%. It's about 3.8 and above. So the value of 49/16, that's only just over 3, that we obtained as our measure of goodness of fit, is outside the critical region. So, from the results of the survey, we have no reason to believe that there's been any overall change in the proportion of Ruritanians who know their Prime Minister's name.
Now let's return to our genetics problem. We've seen how we can obtain a measure of goodness of fit for a simpler example with just 2 counts. In the Morning Glory data, we've got 4. Can we calculate the same sort of goodness of fit statistic? Clearly, yes. The only change to the calculation is that we have to add together 4 separate values of d squared over e instead of 2. Let's see what it comes to. We find each d value, square it, divide by e, and add the 4 values of d squared over e to get our final statistic. The value comes out to 25.09. But how do we test it? With the Ruritanian survey, which had just 2 d values, we had just 1 degree of freedom for chi-squared. But with these Morning Glory data, we have 4 d values, which are, of course, constrained to add to 0. So there are, in fact, just 3 independent d values, and so 3 random normal quantities are involved. Accordingly, the chi-squared distribution of sigma d squared over e has 3 degrees of freedom. Now we can carry out our test.
So this time, we want chi-squared 3. Here it is. And here's the critical region for a significance level of 1%. That will give the model plenty of chance of being accepted. It's about 11.3 and above. But our statistic came to 25.09, miles up the axis and well inside the critical region. There's no doubt that we should reject our genetics model.
So what have we discovered? The genetics model based on independence of characteristics clearly won't fit the data. These expected values are much too low, these much too high. The fact that Mendel's second law doesn't apply to all characteristics based on inheritance from two parents was discovered at the turn of the century. What can then occur is something called genetic linkage. In this case, what that means is that there's a tendency for the pairs of dominant genes to stick together, and likewise for the recessive pairs. Here's the standard theoretical model for this situation. These are our revised probabilities for the occurrence of each of the four types. The probabilities do add to 1, but they incorporate a parameter theta. Of course, when theta's 0, we get the proportions that we tried before, 9/16, 3/16, 3/16, and 1/16. But if we choose a positive value of theta, then this will inflate these two probabilities and send up these two expected values, and correspondingly send down these, which is precisely the sort of effect we want. We've now got to choose an appropriate value for theta. How do we do this? The theory of genetic linkage doesn't dictate a specific value for theta, so we have to estimate it from the information we've got. You've already seen how to do this from the previous unit, where we used the method of maximum likelihood estimation. It turns out that the maximum likelihood estimate for theta is 0.0584, giving these expected values. Here they are. And now the next thing is to use the technique of goodness of fit to see whether these expected values are a reasonable fit to these observed values. So let's work out the differences. There they are. Now we square them and then divide by the expected values. Then we add these four values to give our measure of goodness of fit. It's 0.9. This value of sigma d squared over E is so small, it's clearly going to be well within the main mass of the chi-squared distribution with 2 degrees of freedom. We'll tell you in the post-program notes why the degrees of freedom for this case are 2 and not 3. The reason has to do with the fact that by estimating the parameter theta from the data, we've really reduced the number of choices on the 4 discrepancy values d from 3 to 2. In a situation like this, with the values appearing to match reasonably well, it often pays to do a rough calculation first. We could tell pretty well just by looking that this genetic linkage model adequately fits the data.
So we've seen how one genetic model is not applicable and another is. This has been a typical case of checking theory against observation. In doing so, we've taken you through some simple examples of one of the most important techniques used by statisticians when dealing with frequencies, the chi-squared test of goodness of fit.